A moment in real time tells the history of computers, from the abacus to today's technology, featuring events, pioneers, and inventors who opened the door to extraordinary possibilities. Technology has moved at an explosive pace, so some of the people you will learn about have been virtually lost to history, yet their contributions led to these advancements. To tell the story with so many technological advances over the past 5,000 years, where do we begin? Let's begin at the beginning. Civilizations used different methods to calculate and store information for future use. To keep track of the number of animals killed, they collected small rocks in a pile. In ancient Mesopotamia, modern-day Iraq, people drew lines in the sand and used pebbles to represent numbers. Later, notches and symbols were scratched in animal bone, stone, or wood to record and store information. The use of knots and cords for counting is referred to in ancient Chinese texts and was used by the Incas in South America beginning in 1400 BC. Early counting boards were made out of large stationary stone or marble, and later wood. The smaller portable-style abacus was developed over hundreds of years throughout the Middle East, Europe, and China. These popular styles are still used today. The next major step in mathematical computation was the slide rule. But first things first. Scottish mathematician John Napier devised a method to solve multiplication and division problems by using the much faster methods of addition and subtraction called logarithms. Napier published his research, a description of the admirable table of logarithms, in 1614. In 1624, Henry Briggs adapted Napier's original logarithms to a more common base 10 or decimal numeral system. Some of the earliest computers were designed around the base 10 format. In 1622, William Oughtred created the first slide rule by inscribing logarithms on wood and ivory. The slide rule remained the most commonly used calculation tool in engineering and science until scientific handheld calculators were introduced in the 1970s. French inventor and entrepreneur Charles de Colmar designed and produced the first mechanical calculator in 1820. The calculator was known as the Thomas de Colmar arithmeter. Wilgot Odhner, a Swedish immigrant living in St. Petersburg, Russia, made an improvement in the original design of the Colmar arithmeter. He decided to replace the bulky cylinder with a smaller, lighter pinwheel disc. Odhner patented his calculating machine in 1878 and began mass production until his plant was nationalized in 1917. To the Russians, Felix Dzerzhinsky was the infamous founder of Russia's first secret police, the Cheka, now known as the KGB. At the request of Vladimir Lenin, he established a calculator factory after the Russian Revolution in 1917, using Odhner's patents. Among his countrymen, he and his machine were known by the same name, Iron Felix. In an effort to win the contract to tabulate the 1890 United States Census, Herman Hollerith began experimenting with mechanical tabulation methods. Hollerith formed a company to produce a series of improved machines driven by the need to expedite and simplify the tabulating of vast amounts of statistical data. He got the idea to add a punch card device to his tabulation machine from watching a train conductor punch tickets, called punch photographs. At the dawn of the 20th century, the world was introduced to the small punched-out pieces of cardboard, which create the holes in the punched cards. 100 years later, hanging, swinging, dimpled or rumpled, Chads became a household word during the 2000 U.S. presidential election. Hollerith envisioned boosting the speed and capabilities of his tabulating machine by the addition of electrical energy. An agreement was made with the local trolley company to connect the trolley line electrical system from his workshop each evening after the line closed to test his new electromechanical invention. His tabulating system was the first to make practical use of the punched card in data processing. The cards were automatically tabulated and semi-automatically sorted. Electric wires in the card reader made contact with mercury in a cup to complete an electric circuit and read the data. The electric signal from the contact activated the relevant counter on the panel and caused the hand to register the count. These machines became the nucleus of today's computing industry. In 1910, James Powers, a Russian-born mechanical engineer, was hired by the Census Bureau to design and build tabulating, sorting, and punch card machines. The Powers machines were less expensive and more robust. Data could be entered for the entire card before the card was physically punched, resulting in more accurate output. Powers Accounting Machine Company was eventually merged with other companies and renamed Remington Rand. In 1951, the company delivered the world's first commercially available computer, the ENIAC, to the Census Bureau. The general public was first introduced to the capabilities of these emerging computing machines in 1952. The ENIAC made television history by predicting the winner of the presidential election based on computer analyses of early voting results. Hollerith sold his tabulating machine company, which was later merged with other companies to form the Computer Tabulating Recording Company, or CTR. In 1924, under the leadership of Thomas Watson Sr., CTR was renamed International Business Machines, or IBM. Improving upon Hollerith's designs, IBM continued to produce a full range of tabulating machines. In the 1920s, the IBM 016 duplicating key punch was used in Columbia University's statistical and astronomical laboratories, and later in the IBM Watson Scientific Laboratory. This was IBM's first punch machine with automatic feeding and ejecting mechanisms. A skilled operator could punch about 200 cards per hour. Sorting data into either numerical or alphabetical order is one of the most basic office automation functions. The IBM 080 sorter could sort at a rate of 450 cards per minute. It was the most popular of all the IBM's early office machines. In 1928, IBM made the transition from tabulating to accounting machines with the Model 301. Over the next 20 years, several models were produced, culminating with the IBM 407 accounting machine in 1949. A control panel, or plug board, was wired to specify the calculation details, such as which card columns to read, how to manipulate that data, and how to format the report. Improved printing technology provided a much faster print speed. Introduced in 1937, the IBM 077 collator read decks of cards from the two input hoppers to file new records into an existing set, compare data, remove duplicates, and search for and extract records. IBM developed the 077 to handle the world's biggest bookkeeping job: capture the earning history of every worker so that benefits could be accurately computed and maintained for the newly formed Social Security Administration. The very first punched card tabulating machines were custom built to do just one job, such as tallying the U.S. Census. Starting in 1906, tabulators were made more flexible by the addition of a plug board, also called a wiring panel or control panel, to let users control the actions of the machine. By the 1930s, most machines which used punch cards operated under the control of a plug board. The plug board fits into a receptacle in the machine. This allowed the same machine to be sold into different markets, such as government or railroad, or used for different purposes. This also meant that if the machine was to be used to process payroll, but was needed to process invoices, the plug board would have to be rewired, often a lengthy process that kept the machine offline for extended periods of time. A simple task on an accounting machine might be to print columns of numbers from a deck of cards, in which case a series of wires would connect card columns to printer columns. Programmers used a paper wiring diagram to code the functions to be performed by the machine. Then, the plug board was wired to specify exactly which card columns were to be read or punched. For greater efficiency, IBM began to manufacture machines with removable wiring panels so that programs could be pre-wired and swapped in and out instantly to change jobs. According to legend, the term spaghetti code originated during this era. One of the most successful periods of recruiting for the military was in the 1950s, when training and opportunities in the emerging field of data processing was offered as an occupational specialty. Vacuum tubes were used to create or modify electrical signals. American, British, and German inventors were experimenting with crude forms of tube technology as early as the 1850s. Traditional vacuum tubes were used for circuitry in computing machines. In the 1940s, the Williams tube was designed to electronically store data. Research by famed mathematician John von Neumann led to the development of the IAS machine, which used 2,300 Williams vacuum tubes for memory. Dr. von Neumann also introduced the concept of designing simple hardware, but controlling it by programming instructions. He expanded this to include subroutines, branching, looping, and libraries, which are blocks of programming code which can be used over and over. Dr. George R. Stibitz is internationally recognized as one of the major contributors to the development of the modern digital computer. While a researcher at Bell Labs in the 1930s, he designed an electronic binary adder using surplus relays, tin can strips, and flashlight bulbs. He realized that a relay calculator could perform not just one, but a sequence of complex calculations. Bell Labs recognized a potential solution to the exact problem which was holding back contemporary development of wide-area telephone networks. In the 1940s, Dr. Stibitz pioneered remote computing, a technique that would revolutionize the dissemination of information through telephone and computer networks. Blending an aggressive business model with advances in remote computing technology, Ross Perot founded Electronic Data Systems, or EDS, in 1962. Ross and the EDS team created the world's largest voice data video network and created the trillion-dollar industry, information technology services.
Talking computers and not talking Grace Murray Hopper is like talking baseball and not mentioning Babe Ruth. She was one of the first programmers on the world's first large-scale digital computer, the Mark I. She earned degrees in mathematics and physics before joining the Naval Reserve and attending midshipman's school in 1943. Later, she played key roles in the development of the first UNIVAC computer and COBOL, a business-oriented computer language.
The second major relay calculator development was the MARC series developed by the U.S. Navy, Harvard University, and IBM. Grace Hopper, affectionately known as Amazing Grace, led the Mark I and Mark II development team in the 1940s. She blazed trails and made extraordinary contributions in the development of computers and led the U.S. Navy into the computer age. In the 1930s, she envisioned a computer device small enough for every desk and realized that computers would appeal to a much wider audience if they were user-friendly. Hopper is also credited with introducing the term computer bug to the general public unfamiliar with machine terminology in the 1940s. In September 1945, her team tested the new Mark II relay calculator built at the Naval Weapons Center. A moth flew onto one of the relays, causing a machine malfunction. Creative computer operators retrieved the moth and taped it to the logbook with this statement: "First actual case of bug being found." In 1949, as the Cold War was heating up, the threat was in the sky, and the concern was a Soviet air attack. The military joined with MIT and IBM to design and build the SAGE air defense system. This network of centers around the United States provided for constant monitoring of the sky for enemy aircraft and to deploy fighter jets to defend the country. Technological advances from the SAGE development are still in use today. Dial-up modems, mouse with point-and-click capability, multitasking, redundancy, and interactive graphics. Additionally, the SAGE network was the first major computer-based command and control system, a precursor to today's internet. Drum memory is a magnetic data storage device and an early form of computer memory. Rather than a flat disk, the magnetic drum is a large metal cylinder that is coated with an iron-based recording material. A row of read-write heads run along the axis of the drum. Made of ferrite, or iron, this form of computer memory was developed in 1949 and widely used until the early 1970s. This memory block can store up to 32 bits or 4 characters. The on and off switches are created by having an iron magnet in the shape of a donut intersected by horizontal and vertical wires. A refrigerator-sized stack of core frames equals about 1 megabyte of storage, or 1 million bytes of data. In 1946, ENIAC launched the world into the modern computer age. During the early months of World War II, the U.S. Army entered into an agreement with the University of Pennsylvania to develop a machine to calculate the ballistics firing tables for the new artillery developed for the war effort. Teams of people, known as computers, used desktop and room-sized machines to calculate all the possible trajectories for every tenth of a second of the shell's flight. Each firing table contained thousands of trajectories and took 40 hours to manually calculate. John Mauchly and J. Presper Eckert led the Electronic Numerical Integrator and Computer, ENIAC team, in developing a fully electronic computer, proving that high-speed digital processing was possible. The ENIAC could do 5,000 calculations per second. ENIAC was introduced to the world on February 15, 1946. The ENIAC had 40 primary units, and each had its own arithmetic circuits and program controls. Weighing 30 tons, the ENIAC had 70,000 resistors, 10,000 capacitors, 6,000 manual switches, tens of thousands of feet of copper wiring, and 18,000 vacuum tubes. IBM provided the punch card machines and printer. The ENIAC was manually programmed and required the programmer to determine the entire setup for the problem: sequence of arithmetic operations, function table lookups, and input-output activities. Units were interconnected by cables and setting switches. Some operations were controlled by plug boards. After problem setup, the initiating unit was turned on so that vacuum tubes could warm up. A second switch was turned on to begin the calculation. When the calculation was complete, data was electronically sent to a summary punch, which would punch data cards with the results. The cards were taken to a tabulating machine for printing the output. While men were diverted to wartime service, the Army recruited 6 female mathematicians and challenged them with determining how to efficiently program this new machine. Initially, they were not allowed to see the ENIAC because it was considered top secret. The women determined how ENIAC functioned from its logical and electrical block diagrams, and then figured out how to program it. They created their own flowcharts, programming sheets, and even wrote the program utilizing a challenging physical interface, which had hundreds of wires and 3,000 switches. On February 15, 1946, the Army revealed the existence of ENIAC to the public, using the first mathematical problem programmed by the women. It executed flawlessly and conveyed the immense calculating power of the ENIAC. After the war, the ENIAC was moved to the Army's Ballistics Research Lab in Aberdeen, Maryland. It was used for weather prediction, wind tunnel design, and assisting renowned mathematician John von Neumann with atomic energy research. Despite improvements, the ENIAC proved too costly to maintain. On October 2, 1955, the ENIAC was powered down and packed into wooden crates. The rapid progress of computer technology advanced by ENIAC made the machine obsolete. As we begin the second decade of the 21st century, the ENIAC seems so primitive, but it began the modern computer age and opened the door to endless possibilities in a brave new world.
Let me go back a little bit and say a word about T.J. Sr. My father came back from Columbia one day and said, "Tom, I want you to go right up to that laboratory we have at Columbia." And I said, "Well, why, Dad?" And he said, "Well," he said, "there's a fellow up there doing something very interesting." And I said, "What's he doing?" And he said, "Well, I don't really know what he's doing, but he's doing it at 200,000 times a second." And obviously, the old gentleman saw that something was happening. Later, he knew it was electronics.
Introduced in 1948, the 604 electronic calculator had 1,400 vacuum tubes. It was IBM's first product to use modular vacuum tube pluggable units that performed a variety of mathematical functions. Connected by cable to the 521 card reader card punch machine, it could process 100 punched cards per minute. The IBM 650 magnetic drum calculator was among the first general-purpose computers in the early 1950s. It was programmed in a base 10, or decimal format, compatible with existing data card equipment, and was user-friendly. The 305 RAMAC was the first random access storage machine using disk technology. It was introduced by IBM in 1956. Vacuum tubes were still being used, but much smaller pluggable units replaced the huge single vacuum tubes. Electronic component assemblies could be swapped out easily and quickly. John Bardeen, Walter Brattain, and William Shockley discovered the transistor effect and developed the first device in December 1947, while the three were members of the technical staff at Bell Laboratories in Murray Hill, New Jersey. They were awarded the Nobel Prize in Physics in 1956. Developed as a replacement for bulky and inefficient vacuum tubes and mechanical relays, the transistor later revolutionized the entire electronics world. The transistor sparked a new era of modern technical accomplishments, from manned spaceflight, computers to portable radios and stereos. Today, billions of transistors are manufactured weekly. A transistor regulates electrical current and acts as a switch for electronic signals. Most transistors today are embedded in integrated circuits. As a replacement for the vacuum tube, the tiny transistor gave birth to a new generation of computer technology in the 1950s and 60s. IBM's SMS technology was a way to package transistorized circuitry. In the late 1940s, IBM began development of a new storage and input-output medium to take the place of punched cards. Magnetic tape technology, used for audio recording, was adapted for computer use. The 729 used half-inch tape wound on reels of 10.5 inches. This ultimate first-generation tape drive was used with the very popular IBM 701 and 1401 machines. IBM Corporation recognized the need to increase the power and capabilities of next-generation machines while reducing the physical size and enormous operating costs. In January 1951, planning began for the 701. In less than 18 months, IBM progressed from concept to delivery of the pioneering line of 700 series computers. The most important aspect of the 701 is that it moved IBM into the computer business. Despite internal resistance to abandoning punched card machines, Tom Watson Jr. and the 701 team realized it was a new business with unlimited potential. With the introduction of the integrated circuit in 1958, Jack Kilby changed the world forever. He grew up in Kansas and was introduced to the power of electronics as a young man during a destructive ice storm. His dad managed the local power company, and with all the power lines down, Kilby worked with amateur radio operators to provide communications. During World War II, he was assigned to repair radios for the Army, and later earned degrees in electrical engineering before joining Texas Instruments in the summer of 1958. The idea of miniaturizing electronic circuits was always in the back of his mind, but how? Finally, he realized that all electronic components can be made from the same material on a single site and interconnected to form a complete circuit. In September 1958, he built a prototype of the chip. If it worked, that meant the entire circuit could be manufactured out of a single crystal, making it micro-size, easy to produce, and dramatically reduce the production costs. Of course, the chip that Jack built did work and transformed the way we live. The integrated circuit was an easy sell to the military, eager to build advanced weapons systems, such as the Minuteman missile program in 1962. But businesses and the general public were slow to respond. Texas Instruments recognized the need to accelerate acceptance of this new technology and challenged Mr. Kilby to design a very powerful pocket-sized calculator. And, as they say, the rest is history. Integrated circuit technology restructured communications between people, businesses, and nations, and provided the heartbeat for every modern-day electronic device. For his contribution to the invention of the integrated circuit, Kilby received the Nobel Prize for Physics in December 2000.
We asked Jack how he feels when he sees this photograph of the first integrated circuit.
I feel bad when I see it. It wouldn't have had to be that ugly. If I had known I was going to have to look at it for 40 years, I'd have prettied it up a little bit.
Vacuum tube, transistor, integrated circuit, and in the early 1970s, 3 companies, including TI, developed a microprocessor known as a microchip, or simply chip. A microprocessor is an integrated circuit on a tiny silicon chip that contains up to millions of microscopic transistors and acts as the brains inside an electronic device, such as a telephone or traffic light. Microprocessors allowed for the development of personal computers, initially for the military, scientific, and business use. Weighing approximately 55 pounds and sized slightly larger than an IBM typewriter, the 5100 portable computer was introduced in the mid-1970s. Monitor and keyboard were integrated, and the machine was available with either or both APL and basic programming languages, with data storage up to 64K. Cost of these machines ranged from $9,000 to $20,000. For additional storage, the 5106 external tape drive used a tape cartridge with 204,000 character capacity on 300 feet of quarter-inch tape. On April 1, 1976, Apple Computer Corporation was founded. Apple I personal computer was introduced the next month as a do-it-yourself build-a-PC kit. The Apple II was introduced in May of 1977. The most popular PC, the Apple IIe, was introduced in January 1983. Affectionately known as the Fat Mac, the Mac 512K was introduced in September 1984 and offered a maximum onboard RAM of 512K with a blazing CPU speed of 8 MHz. The retail cost for this machine was $3,195. Add a laser writer printer for $6,995. And home-based desktop publishing was possible for the first time. Software such as McPaint, McDraw, McWrite, and McProject were available and often bundled with the purchase price of the machine. The first laptop computer, manufactured in 1985, was only a terminal, typically used to dial into the mainframe data center through the telephone line to monitor program status or troubleshoot technical problems. Speed of the 1200 baud modem, a device that transmits analog signals, was so slow you could see each page of data appear a line at a time if you paged down the screen. Retail cost for the Informer was $1,900. The new science of nanotechnology allows R&D departments to define the new frontier. IBM has developed a chip for its new Z Enterprise mainframes that is 96 of the world's fastest microprocessors with 1.4 billion transistors and capable of executing 50 billion instructions per second. Intel recently announced a chip the size of a fingernail capable of executing 1 trillion instructions per second. Over the past 50 years, astronauts walked the surface of the moon. The first transatlantic television show was broadcast, courtesy of the Telstar satellite, and the World Wide Web was introduced. In the next 50 years, those who study trends predict exponential growth of wireless and nanotechnology, and a greater blending of humans and computers where nano-neural networks will be the standard. The children of today will grow up in a far more advanced technological world. There will be so much new and transforming information to discover, analyze, understand, and integrate. We're only at the beginning.